Euclid's Division Lemma and Algorithm. In this module, you will learn about Euclid's Division Lemma and Euclid's Division Algorithm. Let's first start with division. We all have been solving division problems. Let's take some real-life examples. Suppose there are 17 chocolates and you had to divide them between 3 friends. Then each will get 5 chocolates and 2 will be left out. Division statement for this can be written as 17 equal to 3 into 5 plus 2. Now think you have 11 chocolates and you want to give 2 chocolates to one student. Then how many students will get the chocolate? 5 students will get the chocolate and 1 chocolate will be left out. Here we have 2 division statements. If we look at these statements, we can say this is just another way of writing 17 and this is another way of writing 11. Consider this division statement. In this 17 is the dividend, 3 is the divisor, 5 is the quotient, and 2 is the remainder. In general, we can say dividend is equal to divisor into quotient plus remainder. For a division, this statement is always true. This means if we divide a number by another, then for the quotient and remainder obtained, this relation is always true. As this relation is true for all integers, this means variables can be used to represent these 2 numbers. If we write A in place of dividend, B in place of divisor, Q in place of quotient, and R in place of remainder, then we will get A is equal to BQ plus R. This generalized statement is called Euclid's division lemma. We have seen when a number is completely divisible by another number, then remainder R is equal to 0, and not completely divisible if remainder is less than divisor B. It implies R is greater than equal to 0 and less than divisor B. Thus, Euclid's division lemma says that for any 2 given positive integers A and B, there exists unique numbers Q and R, satisfying A is equal to BQ plus R, where R is greater than equal to 0 and less than B. We know that HCF of 2 numbers is the highest number which divides both the numbers. We can say we use division to find HCF of 2 numbers. For example, HCF of 56 and 63 is 7. This can be written using division lemma as 56 is equal to 7 into 8 plus 0 and 63 is equal to 7 into 9 plus 0. Can we find the HCF of 63 and 0? We know that 0 can be divided by any number and it gives 0 as quotient. And biggest number that can divide 63 is itself 63 and it gives 0 as quotient. Thus we can say 63 is the HCF of 0 and 63 as it is the biggest number that can divide both the numbers. Now let's find the HCF of 124 and 84. Here 84 is the smallest number and if 84 divides 124 without leaving any remainder, then it will be the HCF of both numbers. As no number greater than 84 will be a divisor of 84. Let's check it. 124 is equal to 84 into 1 plus 40. Here one group of 84 is made and 40 are left over. If any number divides 84 completely, then it will also divide this one group made. And if any number completely divides both 40 and 84, then it will also divide 124. Let's write lemma for this division. When we divide 84 by 40, 2 groups of 40 made and 4 is left behind. And one group of 40 is already there. That means we have 3 groups of 40 and 4 is left over. Now if any number completely divides both 4 and 40, that means it will also divide 124 and 84. Let's see. Out of 40, 10 groups of 4 are made. It implies 4 is the biggest number, which divides both 84 and 124. Thus 4 is the HCF of 124 and 84. Let's understand this geometrically. Here we have a rectangle of length 124 and breadth 84 units. We need to fill this rectangle with square tiles of maximum size. That means a square tile whose side divides length and breadth without leaving any remainder. The tile of maximum size that can be fitted inside this rectangle is of 84 by 84. Let's draw it. If we want to take more tiles of 84 by 84, that's not possible as less area is remaining. This area is nothing but remainder. This remaining rectangle is of size 40 into 84. The square of maximum size that can be drawn within this area is of 40 by 40. We can draw one more square of 40 by 40. This time remainder is rectangle of size 40 by 4. In this remainder, 10 squares of size 4 by 4 can be drawn, and this time no remainder is left. This 4 by 4 square can be made in all the squares made previously. Let's compare what we have done here. First, 124 is divided by 84 and the remainder is 40. In the figure we have drawn square of 84 by 84. That means 84 is taken out of 124. And rectangle of 84 by 40 is the remaining part or the remainder. Here previous divisor is new dividend and previous remainder is new divisor. Now 84 is divided by 40 and remainder is 4. In the figure we have rectangle of length 84 and breadth 40. Out of this rectangle, 2 squares of 40 by 40 have been taken out and a rectangle of 40 by 4 is the remainder. Now again previous divisor, that is 40, became new dividend and previous remainder, that is 4, becomes new divisor. Now 40 is divided by 4 and no remainder is left. In the figure we have new rectangle of 40 by 4. Out of this rectangle, 10 squares of 4 by 4 have been taken out and no part or area is remaining. This means in both the methods, we have done the same thing. This method of finding HCF of two positive integers is called Euclid's division algorithm. Let's recap. Euclid's division lemma says that for any two given positive integers a and b, there exists unique numbers q and r satisfying a is equal to bq plus r, where r is greater than equal to 0 and less than b.